It's right here. Give it.
Oh.
It should be connected. It should connect.
So I noticed this is the camera we're supposed to talk to. Is that why you're doing that?
Let me do this first.
Which is the one recording the video?
They change between cameras
Oh, they changed?
depending on what gives the best angle.
Now, if you want to do the tape, should be good to go. I'm going to test the clicker to see if that makes some sense if you can do.
Okay, hi everybody. I'm going to talk on about algorithms for SSD memory, and it's joint work with my PhD student Tomer Lange, who just defended a few weeks ago, and a colleague Gala Yadgar. We both co-advised Tomer. And it's really good to be here. Thanks for inviting me. Okay, so SSD memory has become very, very popular in the last decade more. It has a lot of advantages. Durable, quiet, small, power efficient. And we have it everywhere in our laptop, phones, data centers, etc. It has several cons. It's expensive. And the biggest worry is limited lifetime. And as a result of that, it has to be managed carefully. Now, the systems community has invested a lot of effort on developing various heuristics for storage system, for these storage systems, SSD, and all these systems conferences where you'll find many, many papers on how to manage an SSD memory. Somehow, the theory community has neglected this line of work, and this is actually what I wanna talk about: how which theoretical problems, algorithmic problems, come up in managing SSDs. Okay, so some SSD basics. So an SSD memory is divided into blocks. Each slot can maintain a page. So a page, for the purpose of this talk, a page is a data unit, and it fits into a slot. Now, a slot in the SSD memory could be either clean, or there could be a page there. Now, if there is a page, there are two possibilities. It could be a valid data, a valid page, or it could be invalid. And if it's invalid, then this is because a new copy of the page has arrived, and and now the old copy is not valid anymore. Okay, the issue with SSD is that we have to do out of place writes. Now, what does that mean? Let's say so now a new page arrives. We write it into a clean slot, and now the old copy of that page is now invalid. Now, let's say we run out of space, or we want to clean some slots in the SSD. So we have to do it at the block level. We have to pick the only way we can't clean a specific location. We have to clean a block. So we have to pick one of the blocks and clean it. So let's say we want to clean this block. The problem is that it has one valid page in it. Ignore the fact that earlier this location became invalid. This is just a bad choice for the animation. So now we'll clean it, and we'll have to move that valid page into a different location in the SSD. Of course, we could use some buffer and keep it at the same location, but anyway, it would be an extra write, and this is called out-of-place writes or a rewrite. Okay, so the motivation for this work, yeah?
So in the previous slide, in hardware, what's the distinction between invalid and clean?
If it's invalid, then I cannot write to it. The question is how is it represented in hardware?
Yeah, we'd expect
It's
free.
it's in the FTL, the flash translation layer. That layer handles these things.
So invalid is not free to use.
Exactly. Yeah, it's not free to use, and it's invalid. It's useless.
Yeah.
Yeah.
It's not free to use because if you tried to write there, something would go wrong and something would happen.
I think you're asking the wrong person.
Okay, all right, fair enough.
You can't write to it. Let's put it this way. Okay, so the problem is, the limitation is that each block can endure only a limited number of erasures, and once we get to that, we erase it that X number of times, then the whole device stops functioning.
So a block is a set of pages or just a set?
Pardon?
A block is a set of pages or a set?
Yeah, think of it as if the memory is a rectangle, then a block is a column in this rectangle. So the SSD management has at least two aspects. One is garbage collection, which I'll focus in this talk, and where the goal is to minimize the number of rewrites. This is called write amplification. I'll define it precisely in a minute. And the other aspect is called wear leveling, and this means that we need to balance the blocks wear where we write. And both of these aspects are handled by the FTL. So if you write in Google SSD write amplification, you'll get, what is it, almost 6,000 results. There are many papers that discuss garbage collection, write amplification, how to optimize it, etc. So let me define our model. So this is our SSD. I'm assuming that we have B blocks, and each block contains n slots, and the logical capacity is P. The number of pages that I'm going to see throughout is P. And the spare factor that we have in the SSD is 1 minus the logical pages over the number of physical slots, which is b times n. So we call this spare factor alpha, and that will play a role in the algorithm.
Capacity include invalid pages or just valid?
This is the number of pages. I'm assuming that there's a fixed number of pages that you're going to see, and then there's a sequence of pages coming, and these pages new versions of these pages will come over and over and invalidate their previous edition, and this number P is smaller than the physical size of the SSD. Okay. Okay, so in this example, n is equal to 4, b is equal to 5, so we have 20 slots, and let's say p is equal to 15, then alpha is 1/4, the spare factor. Okay, as I said before, we have this stream of pages over time. At any time t, some page p is requested, we need to write it, and we have to write it into a clean clean slot in the SSD, and the previous copy is now invalidated. So the algorithm has to make two kinds of decisions. The algorithm for managing the SSD. First, which block to erase, and of course, when. And the second one is where are we going to write the new page P. And the goal is we want to minimize the number of rewrites, and we're going to measure it by this notion of write amplification, which basically measures the ratio between the number of rewrites to the number of writes. Now, the number of writes is, of course, a lower bound on the number of slots that we have to write in the when taking care of a request sequence. And we're looking at the ratio between the rewrites and the writes. We add +1 so that this ratio will always be at least 1. Think of this is similar to competitive analysis, except in competitive analysis we would have liked to look at the ratio between the number of rewrites that an online algorithm does compared to an optimal offline. However, this is not what we're doing. The competitive analysis would be in this context more complicated, and write amplification is very common in this setting of SSDs. Okay, greedy algorithm. What if, let's say, we're in the online setting. We don't know which future writes will arrive. So we run out of space in the SSD. What are we going to do? Well, the greedy approach is just pick a block which has a minimum number of valid slots and clean it. And it's very easy to show that for any request sequence, the write amplification of the greedy algorithm is upper bounded by 1 over alpha. Just to remind you, alpha is the spare factor. And the reason for that is this is the average, this 0.1 minus alpha is kind of the averaging the number of valid slots over the whole SSD, and just by average, looking at the average, we know that the greedy algorithm will not clean more than 1 minus alpha fraction of a block. That's a number of, will not rewrite. That's a number of valid slots. So the write amplification in this case is just the ratio between 1 minus alpha and alpha plus 1, which turns out to be 1 over alpha. And one can show that yeah?
So when you erase a block, so the slots are full, so when you erase the block, are you assuming that you take the valid?
I have to take the valid slots, put them somewhere else, and then write them back. That's the best way of thinking about it, and that's why it's not, the ratio is not going to be more than 1 over alpha. And now I can turn this over this argument and show that I need that any deterministic algorithm is going to, its write amplification is going to be 1 over alpha. And as an adversary, I'm just going to make sure that everything, all the blocks are very balanced. Randomization. So we can show that there is a randomized algorithm. It's not a simple algorithm that improves the write amplification by a little bit. In the denominator, I'm going to have alpha times E minus 1. And just by using Yao's principle with uniform distribution over the arrivals of pages, we can show that the expected right amplification is at least 1 over 2 alpha for any randomized algorithm. So that leaves a small gap for randomized bounds. Okay, let's move beyond just the greedy algorithm. So given a request sequence, I want to view it as inducing an interval graph. Now, what is this interval graph? Well, let's say we get a request. So for page P, it's born here and it dies here. What does it mean that it dies? A new request for the page P arrives. So I'm thinking of this request for P as defining an interval over time. And every page defines a sequence of consecutive intervals over time. And over all of the request sequence, I get an interval graph. So, and now I have to decide where to place the intervals and which blocks to erase. So let me do a digression and to the pure offline problem, and let's ask the following simple decision problem. When can a request sequence be handled, assuming everything is given in advance, so that there are no rewrites at all? So this can be related to a problem called lambda comma C fragmented coloring, defined by Kleinberg et al. In the context of databases. And in a general problem, the lambda C coloring problem is the following. I want to color the nodes of a graph with lambda colors so that the size of every connected component is at most, monochromatic connected component is at most C. Turns out we can show that this problem, deciding whether a request sequence can be served with no rewrites at all, is equivalent to finding a fragmented coloring of the interval graph induced by the request sequence with the parameters B, number of blocks, and N, number of slots in a block. Unfortunately, the status of this problem, fragmented coloring in an interval graph, is open. And more generally, the status of minimizing the number of rewrites of a request sequence is also open. We don't know whether it's NP hard or it can be solved polynomially. Okay, so as I said before, we need to decide, an algorithm has to decide which block to erase and where, given a new request, where to write it. Which block to erase? A greedy choice is pretty reasonable. Where to write a page? This is more complicated, and this is going to be the focus of this talk. So this is our picture. This is the SSD memory, and these are the valid, the blue slots are the valid slots, valid pages. And ideally, I would have liked it to look like this. Either I have blocks with lots of valid pages, or I have blocks with very few invalid pages. Of course, I'll erase one of these blocks. And so this is an ideal picture, and the question is how can I achieve it? Because clearly, if I can maintain this picture, then the garbage collection overhead is going to be minimal, very few rewrites, and well, given the lower bounds on any online algorithm that we've seen in the previously, we will need some hints about the future. Otherwise, we're stuck with these bounds. Okay, so to achieve this ideal picture that we just showed, we're going to group similar intervals in the same block, and the question is, what's similar? You can think of three natural choices of similar. One is birth time, other is death time, and the third is just the lifetime. The length of the lifetime is just the length of this interval. Okay, so grouping by lifetime, I would group the two green ones together, the two red ones, and the two blue ones together. That's probably not a very good way of grouping, because this information is available to the any online algorithm, assuming no other information is available, then all the online lower bounds apply here. Then there are two other options, grouping by death time. In this instance, it would be here, these two greens together, the two reds and the two blues together, or by lifetime, which would give a different grouping. And I'm going to concentrate on these two choices, death time and lifetime. In the talk, I'll present an algorithm that is going to use death time, and then an algorithm that's going to group according to lifetime. Okay. For ease of presentation, let's assume we're still in the offline setting. Everything is known in advance, and I'm going to develop an algorithm, and then we'll see how to transfer it to an almost online setting. So grouping pages according to similar death times has been suggested earlier in the systems community, and the motivation is clear. If we do that, then these pages are which are grouped with very, very close death times. If I group them in a block, they're going to die very close to each other, which is, as we have seen, it is a good thing. So how do we achieve that? Well, we can sort intervals in increasing order of death times, and write them to the blocks in this order. The problem is what happens with erasures, rewrites. Of course, if I look at these two intervals, well, the problem is, I mean, here they're not very close to each other, but in principle, if I have one interval which is contained in another, then if they're in the same block, then they're not going. it's going to be a problem in terms of the whole block expiring, and I really don't know offline how to solve this problem. So let's see what we can still do. So let's see the first offline algorithm. So we have this while loop which starts as long as I have completely invalid blocks, which means that all the pages in the block are invalid. I'm going to erase all these blocks. I don't incur any rewrites. And now I have this clean space. And I am going to write, suppose I have 100 clean slots now in these blocks that I just cleaned. Then I'm going to take the next 100 pages in my request sequence, which I know in advance. I'm going to sort them according to their death times and write them to the blocks in this order. So assuming these numbers indicate the death times, then this is how I'm going to write them into the blocks. So this while loop repeats as long as I have completely invalid blocks. And once I don't have complete invalid blocks anymore, I'm going to the current phase ends, and a new phase will start. I'm going to erase all blocks and just group all the valid pages according to their death times. Okay, so this is the algorithm. Now let's see how we can analyze the right amplification of this algorithm. So here, a new phase starts. These are the invalid blocks that I'm going to clean, and I'm going to write, in this case, I have 8 slots in this example, so I'm going to take the next 8 requests and sort them according to their order and death time and write them in that order into these blocks. So what is the situation right now? These were the result of the new phase. I grouped all of them. And these blocks are sorted in this area. They're sorted with respect to each other. And same thing here. Also, the blocks are sorted with respect to each other, but it's not true between these pages, these blocks, and these blocks. Now I run an iteration of the while loop. As a result, when the iteration ends, some of these blocks will become invalid, and some of these blocks will become invalid, but I'm going to have a hybrid block generated from these guys. A hybrid block is a block where I have both valid and invalid. So I'll have at most one hybrid block from this group or batch, and I'm going to have at most one hybrid block from this batch. Now, in the next iteration of the while loop, I'm going to generate another hybrid block which is the result. These two blocks are now cleaned. This block is cleaned. So these three blocks will contain the next batch. After I iterations, I'm going to have I batches. In each batch, the blocks are sorted with respect to each other in terms of the order they die, plus at most one hybrid block. So let's see how we estimate the right amplification. So a phase starts with alpha B completely invalid blocks which are cleaned. After I iterations, there are at least alpha B minus I completely invalid blocks because every batch has at most one hybrid block. So the number of writes in a phase is at least the sum from I goes from 0 to alpha B of n number of slots times the number of blocks that I'm going to clean in the ith iteration, and I get this value. What about the number of rewrites? Remember that during the execution of the while loop, I'm only cleaning blocks that are invalid, so no rewrites are incurred. So the only rewrites are when we move to a new phase. So the number of rewrites is at most p, the number of valid pages. So we get that the right amplification is 1 plus O of 1 over B. Okay. Now, so far we've been in the offline setting. Now I want to move on to a learning augmented setting where I get some hints about the future so that I can implement the offline algorithm that I've shown you in the online setting. Well, what kind of information can help us? Answer is clear. Death times. I need the death times to implement this algorithm. So my prediction model is that each request comes with a predicted request R comes with a predicted death time, which is y hat of R, and the error for every request is just the absolute difference between the real death time and the predicted one, and the total error is just the L1 distance, which is the sum of the individual errors. Okay. So now let's see what happens here. So we're using predictions. Now the problem is this is my SSD. The numbers indicate the death times, and now comes a new request which has death time 5. It makes sense to write this new page either here or here. Both are consistent with what I want to achieve, but I don't know where to write it. So I need more information than just the death time in the online setting. So the way we come around this is having an additional memory, a non-SSD memory, where we simulate the offline algorithm over there, not the whole offline algorithm, just the part that we need for the extra information. And we can show that the right amplification is 1 plus a term which depends on 1 over m plus a linear term in the prediction error divided by the length of the sequence. So here we have a linear dependence, and over there we have the dependence is inverse in the size of the memory, so the more memory we have, the better the right amplification is. So this is fine, but we were not very happy with this need to have an extra memory. So we moved on to a different grouping, which is grouping by lifetime and having fixed classes, which are independent of the input sequence, unlike grouping with respect to death times. And this is kind of generalizing the hot-cold separation which people in systems have been doing for quite some time. And of course, this is a more general partitioning into classes is of course a classic principle in scheduling theory. Okay, so let's get, huh?
2 minutes.
2 minutes? Okay, I'll try in 3 minutes. If I have a sequential input, which means that it implies a proper interval graph, then I can, all I need is just one buffer, one extra block, and once I erase it, everything is going to move forward. So intuitively, since I have alpha B spare blocks, I can support alpha B streams of sequential writes. And of course, in practice, the writes are not sequential, so I'm going to divide the input sequence into, let's call it, almost sequential subsequences. In earlier works in the systems community, they have used exponential partitioning, and then the reason why this doesn't work so well is that you have too few classes, and of course you can make mistakes between hot and cold, and that can get you into trouble. What we were doing is a large number of classes which are linearly increasing, so the classes, the lifetime classes are delta, 2 delta, 3 delta, etc., up to k delta. K is remember the number of the spare factor alpha b, and then all of the other requests we just batch them together here, and we call this the last class. And now our offline algorithm works like this. We get a new request. We classify to which class it needs to go. And then there's always, for every class, there's one active block where we place that request. What happens when that active block becomes full? Well, then we have to do garbage collection. We either erase a completely invalid block, or we greedily steal a block from the last class. That's where all the long lifetime pages are. We clean it and use that block. Let me skip the analysis here. Just tell you what the result is. So the result is very similar to what we had with grouping by death times. However, we can implement this. We can implement this algorithm with in the online setting by just having the death time prediction, and the bound we get is we don't need any extra memory, and the right amplification increases logarithmically and not linearly as before. And we can show that the prediction error is or the right amplification is optimal with respect to the total prediction error. Okay, so just to wrap up, we did some experiments which have shown that this last algorithm, which we called Gladiator, performs much better than other algorithms. Let me, 10 seconds, I'll tell you some other work we've been doing on SSDs and PCM. So one is on wear leveling, where we show how to combine both wear leveling and garbage collection, using garbage collection as a black box with a very small increase in the right amplification. And the other line of work is on caching, where we want to simultaneously minimize the miss rate as well as the number of memory writes, including, of course, rewrites. Okay, so I'll stop at this point. Thank you. Yeah.
One question would be like, how good the predictions still be for online?
How good are they, or where do they come from?
Both, like I can understand how you can predict
Well,
and be accurate.
Okay, of course you cannot be very accurate, but in this, the machine learning has a lot of power, and so that's one thing. Also, systems people have been doing predictions even before the era of machine learning predictions, and of course we have you will have errors, and if we looked at the picture with the experiments, as long as the prediction errors are small, our algorithm Gladiator actually performs well. It stops performing well when the prediction errors are, in certain settings, when the prediction errors are large. But having large prediction errors is like having no information about the future. Dave?
Hey, so I mean, you and I talked about this work at SWA.
Oh, SWA, yeah, that's good.
You know I love it.
Pardon?
You know I love it. I was going to, just for discussion.
Thank you.
In this room, I was going to say, like, one thing that has come up in actual SSDs is this thing called zoned namespace, which basically force you to say in advance, not when the pages are going to die, but to say all of these pages will die together. So, for example, you might say all these pages are part of a file. I don't know when it's going to go away. That's up to the user, but I know it's going to all go away together.
And then you want to put them in the same block.
Right. And in fact, that constrains you. You have to erase them together. But I think a really interesting direction, which I can think of actual applications, would be imagine to adapt your work to where you don't predict death time, but you predict similarities of death times or something like that. You don't know when, but you just say, well, these are likely to die near each other or something like that.
Okay.
That'd be a blueprint.
Thanks. Yeah, Phil?
So it feels like one natural prediction, and I wonder if you study these experiments. So this is, these are pages that are getting written again and again and again. So you can always use some statistic on what's happened today to predict the next lifetime, right?
Right.
It seems like a very pragmatic scheme. It could be just even what was the very last lifetime, or some average over. Did you study that? Is that?
Well, we're using it as the prediction as a black box. We're not.
Yeah, but when you were doing the experiments, did you actually look at a real
So what we just
prediction mechanism?
in the experiments we decided on the death times, and then we just used some stochastic. We just introduced errors stochastically. That's the way we did the experiments. We didn't choose a particular, and that introduced the errors. We didn't use a particular way of prediction.
I guess building on that, I think your algorithms are sort of agnostic to the identity of the pages, right? So what happens to a page?
Why agnostic? I
When agnostic meaning, like in this case, Phil is saying, okay, that particular page has certain characteristics over time that you can.
As a result, the prediction will be so and so.
In your case, the way you're using the prediction is there is a page coming, then it gets hit, then it's written. So that has no implication on what happens next to the page. So it's as if it could be a different
in the
page.
next edition of the page.
Yes,
I mean,
it could be just a different page for all you know. I mean, it's,
I'm not looking into this, but the predictor could in principle, could use that.
that could benefit, yeah.
Yeah.
So in the last slide about using death times, like you have this 5 that goes either to the column with 3 or with 7. Would you like to go intuitively like with 7, so that you allow those ones that will die soon to give you a free column there, so that you can.
But maybe I'll get a 6 afterwards, after the 5.
Yeah.
It happens sometimes. That's why we use the extra memory to simulate the lack of information.
Yeah.
Do these algorithms still maintain the 1-over alpha amplification?
Sorry?
Do these algorithms still maintain the 1-over alpha amplification?
Yeah, it's a graceful degradation, definitely, yeah.
Great. Thank you.
Okay.
Quick word about the schedule for the rest of the day. So there's a long lunch break until 3. This is a feature, not a bug. There's one more talk session from 3 to 4. Normally we kind of start on California time, but there's a reception at 4. So like try to get back here at 2:55 or something. With this one session, we're going to try to start on time from 3 to 4, and there's reception afterwards. All right, enjoy your lunch.